I welcome each one of you to this video, and we would be continuing the discussion on relations. So with this, let's move ahead. So in first video, we had talked about ordered pair, partition product, and relation. All right. In next video, we had talked about different ways to describe or define or declare a relation, domain and range in a relation, inverse relation, empty relation, universal relation, identity relation, and total number of possible relations between two sets. In this video, we are going to talk about a typical classification of relations as reflexive, symmetric, transitive. And if a relation is all the three, reflexive as well as symmetric as well as transitive, it is called equivalence relation. All right, so let's start with the understanding of reflexive relation. All right, so a relation is called reflexive if each entry of A is related to itself, but not necessarily only to itself. All right. In previous session or previous video, we had talked about identity relation. In identity relation, it was required that each element or each entry of A is related to itself and only to itself. Here, uh, each entry of A should be related to itself, but not necessarily to only itself, but not necessarily only to itself. All right. So by this we mean if A comma B is belonging to relation, then for R to be reflexive, A comma A must necessarily be in the relation R. All right. So let's take some examples. Say A and B are natural numbers and they are related as A is the divisor of B. Now, uh, 2 is the divisor of 4. In fact, 2 is the divisor of itself also, right? So 4 is the divisor of itself also. So this relation is reflexive in nature. All right. Let's take another example. Let L be a set of lines. All right. And two lines, which I'm calling them as L1 and L2, both of them belonging to the set L, are related such that L1 is parallel to L2. Now, L1 is also parallel to itself, though it is coincident. However, they are parallel too. Why? Because they have the same slope. All right. So here is there is an important point that I am sharing with you. Every identity relation is reflexive. However, every reflexive relation is not identity relation. Just see this. Here, this is a reflexive relation because 2 is related to itself, 4 is also related to itself, so on and so forth. However, what about these elements, these ordered pairs, 4, 8? Since this is coming, this relation is not identity relation. Why? Because in identity relation, as we had seen in previous video, an element should be related to itself and itself alone. All right. So similarly, this second, it is a reflexive relation but not identity relation. So just to repeat, every identity relation is reflexive. However, every reflexive relation is not identity relation. All right. So let's let me ask you one basic question. It's just coming to my mind, so let me ask you. All right. Let's say there is a relation R which has these ordered pairs 1, 2 and 2, 3. All right. Now, how many more elements or ordered pairs should be added to this set R so that it becomes reflexive in nature? Think about it. It's very simple. 2 ordered pairs I need to add. What all? I need to add, let me change the color so that I need to add 1, 1 and 2, 2. Why? Because if A comma B belongs to relation, then A comma A must necessarily belong to that relation so that it becomes reflexive. So since 1, 2 is belonging to the relation, 1, 1 has to be part of that relation for the relation to be reflexive. Similarly, 2, 3 is part of this relation. So 2, 2 should also be part of this relation for this relation to be reflexive. All right. So with this, let's move ahead to symmetric relations. All right. A relation defined from set A to set B is said to be symmetric if A is related to B, then B should also be related to A. All right. In previous reflexive thing, we had seen if A comma B belongs to this relation, rather we can say it as if A is related to B, then A should be related to itself also. Similarly, here in symmetric relation, if A is related to B, then B should be related to A for the relation to be symmetric. All right. So this is the same thing which is being repeated, right? If one ordered pair A comma B is there, then another ordered pair B comma A should also be present in the relations for it to be symmetric. Let's consider this first example. Set of lines. L is set of line. L1 is related to L2, where L1 and L2 both belong to this set L of lines if and only if L1 is parallel to L2. Now this is symmetric as well as reflexive. Why? Because if L1 is parallel to L2, L2 is also parallel to L1. So this is symmetric. All right. And reflexive, we have just seen in the previous slide. All right. Now let's again consider set of lines where two lines L1 is related to L2 if and only if L1 is perpendicular to L2. Now see here, this relation is symmetric but not reflexive. Why? Because L1 is not perpendicular to itself, right? However, if L1 is perpendicular to L2, L2 is also perpendicular to L1, right? So this relation is symmetric but not reflexive. All right. So let's move ahead. All right. Let's consider this question. If small a belongs to capital A and small b belongs to capital A again, where A is set of family members, then which of these relations are symmetric in nature? Think carefully. Please pause if you so want and think about the answer to these two parts of the question. All right, and then get back to the video to know the right answer. All right. A related to B if and only if A is brother of B. Is it symmetric? No, it is not symmetric. Why? If A is brother of B, it is not necessary that B is also brother of A. B may be sister of A, yeah? Come on, right? All right. In the second relation, A is cousin of B. And is it necessary that B is also cousin of A? Yes, it is necessary, right? So the second relation R2 is symmetric, while the first relation R1 is not. All right. Let's consider this. Let R equal to 1 comma 1, 2 comma 2, 3 comma 4, 2 comma 3. This is the set of the relation. At least how many elements need to be added to this set R, to this relation R, so that it becomes reflexive and symmetric? All right. All right. So first thing that should come to our mind is this 3 comma 4. So that means 3 comma 3 should be there, right, for reflexive, right? At the same time, 4 comma 3 should also be there for symmetric. 3 comma 4, so 4 comma 3 should also be there for symmetric. Now since 4 comma 4 has to be there, then that means 4 comma 3 has to be there. So that means 4 comma 4 also has to be there for reflexive again, right? All right. And now 2 comma 3 is there, so 3 comma 2 should also be there. Here we can note that 2 comma 2 is already part of it, and 3 comma 3 we have already considered. 3 comma 3 we have already considered. So these four elements need to be added to this set for this set to be reflexive and symmetric. All right. All right. So let's move ahead. When such questions are asked, you may pause the video and try out yourself so that you can check whether you are right or not. In case you find you are right, it will boost your confidence. All right. So let's move ahead and learn about transitive relations. All right. A relation is said to be transitive if A is related to B and B is related to C. That should imply A is related to C. Then that relation is called transitive. All right. Now here the point to be noted is A, B, C needn't be distinct. All right. Also another point to be noted is that relation is not transitive only when A is related to B and B is related to C, but A is not related to C. That's the only possibility for a relation to be not transitive. All right. So just to repeat, relation is transitive when this kind of thing is implied. A is related to B and B is related to C should imply that A is also related to C. All right. All right. So let's you may pause the video and answer this question. Are the following relations transitive? Let me answer them for you. All right. R is equal to 1 comma 2. Is it transitive? Yes, it is transitive. Why? Because it is only one element, 1 comma 2. That's it. So a relation is not transitive only when this thing happens, right? This is what we have discussed. So this first relation is indeed transitive. What about second? 1 comma 2, 2 comma 3. No. Why? Because 1 comma 3 is not present, right? Because if 1 is related to 2, 2 is related to 3. That means 1 should be related to 3, which is not here. All right. What about the third one? 1 comma 1, 2 comma 1. Hi, this is interesting. Is it transitive? Yes, it is transitive. How? See, 1 is related to 1, 2 is related to 1. So with this sequence, it is transitive. Now let's check the other way around. 2 comma 1, 2 is related to 1 and 1 is related to 1. That means 2 should be related to 1, which is already so, right? 2 is related to 1. Let me say this is A, this is B. So this is B, this is C. A is related to B, B is related to C. So A should also be related to C. But here B and C are the same, 1, 1. All right, I hope you got it. So this is transitive. All right, what about this? Identity relation 1 comma 1, 2 comma 2, 3 comma 3, so and so forth, 4 comma 4, so and so forth. All right, this is also transitive, right? Because 1 is related to 1 only, 2 is related to 2 only, 3 is related to 3 only, and this thing is not happening. Okay, so this relation is transitive. Let's move ahead. All right, a few examples of transitive relations. A and B are natural numbers. A is related to B if and only if A is less than B. Okay. Now this is transitive. How? Say A is less than B and B is less than C. This would imply that A is less than C. That means A is related to C. That means if A is related to B, B is related to C, this implies A is related to C. So that means this is transitive relation, hence the example for it. All right. Let's take that question here. Set of family members, A and B both belong to that set of family members. These both are transitive. How? If A is brother of B and B is brother of C, that implies A is brother of C, right? Because if A is brother of B and B is brother of C, so that means A and B both are male. All right. Now, since B is also brother of C, and A is anyway brother of B, that means A is brother of C. But it doesn't imply that C is brother of A. Why? Because C can be a female, right? A is brother of B, B is brother of C, right? That means A is also brother of C. So this is indeed a transitive relation. All right. What about A is cousin of B? This is also transitive relation. Why? Because if A is cousin of B and B is cousin of C, that means A is also cousin of C. All right, so let's move ahead to equivalence relation. Now, a relation is called equivalence relation when the relation is reflexive as well as symmetric as well as transitive. When relation is symmetric also, reflexive also, and transitive also, then that relation is called equivalence relation. An example is identity relation. It is reflexive, it is symmetric, and it is transitive also. All right. So identity relation is an example of equivalence relation. What about this example? L is a set of lines where L1 is related to L2, where L1 and L2 both belong to the set L, L1 is related to L2 if and only if L1 is parallel to L2. It is an example of equivalence relation. Why? First of all, a line would be parallel to itself because a line is having the slope which is same in both cases, right? So we have just seen that this is reflexive, this is also symmetric. Now, what about, is it transitive? Yes, it is transitive. If say L1 is parallel to L2 and L2 is parallel to L3, that would mean L1 is parallel to L3. So that means it is transitive also. And we have already seen that it is reflexive and symmetric, right? So that makes it an example of equivalence relation. What about set of triangles? Where T1 and T2 belong to this set of triangle. T1 is related to T2 if and only if T1 is similar to T2. That means T1 and T2 are similar triangles. Now, a triangle would be similar to itself. In fact, it would be congruent. So it would be definitely similar to itself. All right. If T1 is similar to T2, T2 is also similar to T1. So it is symmetric, right? What about transitive? If T1 is similar, let me use standard notation only. All right. If T1 is similar to T2 and T2 is similar to T3, all right, triangle T1, T2, T3, that means T1 is similar to T3 also. That means this and this would lead to this conclusion also. So that means this is transitive also. So that means it is an example of equivalence relation. What about this? This is, I would say, a good example. A and B are natural numbers. A is related to B if and only if A plus B is even. Now this is indeed an equivalence relation. How? Uh, if A is definitely related to A. Why? Because A plus A would always be 2A. So that means it is even. All right. So this relation is reflexive. What about symmetric? A related to B. Does it imply B related to A? Yes, B related to A. Why? Because addition is commutative. If A plus B is even, B plus A would also be even. All right. What about transitive? Let's check this out. If A is related to B and B is related to C, it implies A is related to C. How? First of all, this A, B, C, these are natural numbers. All right. So either A can be odd or even, right? For A to be related to B, that means for A plus B to be even, either A and B both should be odd or A and B both should be even. All right. Same with B related to C. Either B and C both should be odd or B and C both should be even. So in any case, if A is related to B and B is related to C, A, B, C are all odd or A, B, C are all even. So that would imply that A is related to C also. Because if A and C both are odd, then the A plus C will be even. And if A and C both are even, then A plus C is even again. So it is transitive also. So that means this relation is indeed equivalence relation. All right, let's take a couple of questions before we say goodbye. All right, we have to comment whether this relation is reflexive or not, symmetric or not, transitive or not. Again, you can pause your video to answer it yourself, and then to check the answer, get back to the video. All right, so let me answer it for you. First of all, whether is it reflexive or not. First of all, 1, 2 is coming. Hey, 1, 1 should be there. Hey, it is indeed there. It is indeed there. 2, 2, all right. 1, 1, all right. 4, 4, all right. 1, 3. Hey, 1, 1, 3 is coming. 1, 1 should be there. It is there. 3, 3 is all right. 3, 2. So 3, 2 is there. So 3, 3 should be there for this relation to be reflexive. So it is indeed there. So that means this relation is reflexive. What about symmetric? 1, 2 is there. So 2, 1 should be there. Hey, 2, 1 is not there. That means it is not symmetric. Now, what about transitive? Transitive is interesting of all the three generally. All right. To check transitive, 1 is related to 2, 2 is related to 2. That means 1 should be related to 2. It is already there. All right. So 1 is related to 1 and 1 is related to 2. So that means 1 should be related to 2. Again, it is there. All right. All right. So 1 is related to 3 and 3 is related to 3. That means 1 should be related to 3. It is already there. 1 is related to 3 and 3 is related to 2. That means 1 should be related to 2 for a relation to be transitive. It is there here. All right. So 1 वाले तो हो गए. Now 2 वाले, 2 is related to 2 and is related to 2 only. So here it is transitive, no issues. All right. Now 3 is related to 3 and 3 is related to 2. So 3 should be related to 2. This is already there. And 4 is related to itself only, 4. So it is indeed transitive. All right. That's it. So this is how you check whether a relation is reflexive or not, symmetric or not, transitive or not. All right. Now, oops, somehow answer is already in front of you. However, it would have been an interesting question, all right, for you to solve, all right. Nonetheless, this is a given relation and we want to add minimum number of ordered pairs so that R turns out to be equivalence relation, all right. A similar question, short version, we had done for reflexive. I had given one problem to you and we discussed that, right? All right, so let's discuss this problem, all right. Unfortunately, answer is here. It was not supposed to be anyway. So that means we have to add 7, right? 7 more elements or more ordered pairs to make this relation R or set R to be equivalence relation. All right. So let's check it out. How do we get this? First, we consider reflexive. Rather, we consider all three, but we should start in general with reflexive and come back to reflexive again and again whenever it is required. Let's check it out. It will be clear. So 1 comma 2, 2 comma 3. All right. So 1 comma 2 is there. So 1 comma 1 should also be there. Great. 2 comma 3 is there. So 2 comma 2 should also be there. Great. All right. Now 1 comma, now coming to symmetric. All right. Reflexive, symmetric, transitive. 1 comma 2 is there. So that means 2 comma 1 should be there. Right. 2 comma 3 is there. So 3 comma 2 should be there for for it to be symmetric relation. All right. All right. Now, but now coming to transitive, 1 comma 2 is there, 2 comma 3 is there. So that means 1 comma 3 should be there. So 1 comma 3. Here, let's revisit to the reflexive part. 1 comma 1, 2 comma 2, 2 comma 1, 3 comma 2. Hey, 3 comma 2. So that means 3 comma 2 is there. So 3 comma 3 should also be there. It's there. All right. And till now, it is reflexive as well as symmetric. All right. No, it is not symmetric. Why? Because 1 comma 3 is there. So 3 comma 2 is there. So 2 comma 3 is there. But what about 1 comma 3? 1 comma 3 is there. So 3 comma 1 should also be there. So that it is symmetric. That's it. And now it is reflexive, symmetric as well as transitive. You can check it out. All right. 3 comma 2, 2 comma 3. So 3 comma 3 is there. 3 comma 2, 2 comma 1. So 3 comma 1 is also there. So and so forth. So it is reflexive as well as symmetric as well as transitive. So this makes R an equivalence relation. All right. So we had to add at least 7. We should add at least 7 ordered pairs to make this R an equivalence relation. All right. With this, next slide has just the answer to this question, which already has been featured in this slide only. So let me thank you. I thank you for your patience, for your attention, and for being there with me in this video. Thank you. Have a nice day.